And we've got some, accompanying information as well. So we'll get started with everything. Again, everything's recorded, by the way. So if anything does happen or anything goes wrong, we'll be able to access all of this information, and you can come back to us when needed. Before we get started, just a little bit about ourselves. So my name is Hashan Mendes. I'm working at Leap Australia. We're a trusted partner. Founded around 1996, 50 people around Australia and New Zealand, with thousands of clients, including 95% of the actual tertiary education institutes as well. We're not just about selling software, so we're a channel partner for softwares around Australia and New Zealand. We also do things like this: training, technical support, consultancy, and guest lectures as well. So, feel free to stay connected below. I'll send everyone a link to all of these slides. So, have a look at our social medias. As an example, we post, things that are happening in the industry, also things like careers as well. So we're actually looking for technical salespeople at the moment around Melbourne and Brisbane. And we've always got things available for careers, for internships as well. So if you are interested and this is kind of what you're doing, please do support us. Get on the social medias and send us a message as well. You can also Google Leap Careers and you'll be able to come to this page. All right. What I'll do. Sorry, I can just hear some chatter every now and then. I'm just going to mute people. We'll just take it from there. Before we get into the fluid dynamics, I just wanted to have a once over about, again, a little bit more. So Ansys, what we do, we support Ansys software as well as things like PTC and a source of other softwares as well. All of these around, engineering applications and design. All right. There are a lot of companies around the world that are actually leveraging the actual platform that we're using. So a lot of the information that you're learning now as a graduate, they're going to be useful come in your actual career, depending on whatever you want to do around the world and throughout the industries as well. One of the reasons that a lot of people are using simulations is a couple of factors that we can kind of see on the screen. So the time to market of these products is increasing, the actual life cycle is decreasing as well, and we've got new products that are coming out. One of the reasons that we're using simulation is because on top of that, products are actually getting more complex. Again, they need to be delivered faster, and the quality of them needs to start to increase as well. One of the reasons we've partnered with Ansys is because of the breadth of what they've actually got. So they've got a full platform based on materials informations, fluid structures, and electromagnetics as well. There's a lot to do with Ansys. We even do things like optical. We're not going to go into that much detail in this particular training, but if it is something that you're really interested in, please do let us know. Like if you've got a project, and I can always get you in touch with the people that can really help you out, or we can actually get in touch with the Ansys team directly and get them to help you out, right? So, what are we really trying to do here as well? Now, as well as a platform, but as well as your kind of career as an engineer, at university, you've probably started off learning and understanding about single physics. So you guys have probably got, CFD or FEA classes. What happens is that if you choose to go down this route, you will start to learn a little bit more. You'll start to combine the physics together. We can have, tightly coupled or loosely coupled simulations. So multi-physics or multiple physics simulations. What happens is that when we've got these components, we've got designs out there, and we're using these simulations, we've got CAD information as well. They start to form what's called this digital prototype. When we've actually got the full product made, we've got what's called a complete digital prototype. And what happens is that when it's actually out there on the field, we've got what's called a digital twin. So we can actually start to take information from what's out there in the field, pair it back to the analysis and what we expect to happen, and get a deeper understanding about the actual product, what's happening with it at the moment, is it within the design capabilities, and what do we need to do going forward? Are there potential warranty problems, or can we make aftermarket accessories for it? So the training that we've got over the next couple of days, so this first week is going to be focused on fluids, next week is going to be focused on FEA, and the week afterwards is going to be focused on electromagnetics. We've got kind of 2-hour sessions broken out throughout the day. So what we'll try to do is go over the presentations as well as actually get some hands-on with the software. And then we've got some online training material as well. And then what you can do afterwards is that depending on how much you want to get into it, you can go through all that, and then you can actually call us back on support if you need to, and we can actually help you out with your projects if you've got engineering teams or anything like that. As a bit of an overview, so we're going to go through the kind of the introduction, some of the meshing side of things as well as the basic physics. But you can see on the left-hand side, we've got a lot of different things that we can, play around with. So on the top here, we've got a fluids analysis. So this is a thermal analysis, right? This could be something like a battery pack trying to understand what the efficiency is. We've got a mixing analysis on the top right? So again, we can have a look at the design and understand how is the cement actually mixing. On the bottom left, we've got a water. So this is a volume of fluid. Again, we can analyze things like boats, and traditionally people I'm sure are aware of external aerodynamics. So you can see on the bottom right, again, we've got a car, right? We'll talk about in a little bit more detail some of the structural physics and the overview as well, right? So how it's used. So if we've got explosions, if we've got crashes, you can see making these types of components and demolishing them again and again can obviously be very costly. So we can use simulation to really reduce the actual design impact. Topology optimization and rigid body dynamics as well. Again, all of these things are simulations that we can do within Ansys. And we've also got a suite of electromagnetic tools. I'm not going to go too deep into that. It's not really my expertise, but if you do have any questions or you want to incorporate, some electromagnetics into your structures or your fluid simulations, again, have a chat with us afterwards. Like we're talking about, we learned a lot about the simple single physics side of things, but when we start to get a little bit more advanced, we can actually start to pull a lot of these things together. So you can see this is a little bit of a step-by-step about what we might want to do. This is a fluids structural analysis. So initially we've got some sort of fluids analysis, and it's giving us information about what's happening with the actual pressure on the surface. We can take those forces and we can do a structural analysis afterwards, right? Whether that's stress strain, we're looking, and in this particular case, we're actually looking at the modes. We can then start to understand if there are any resonant frequencies, and we can start to have a look at what the potential stresses of the actual simulation might be. We can start to ask ourselves, how long will this actually come into play? How long will this live? Are there any hotspots? And if we identify any of those, we can then start to make some changes as well with the actual design. All right. So again, there's a huge amount of tools that we've got underneath our actual belt, depending on what you want to do. It can get pretty intimidating. So, we always encourage students come talk to us early on in the design process, have a conversation with us. And, if this is something that you're going to do and this is a part of your project, we can make sure you've at least got the correct material or you're on the right path, or the actual expectations that, are actually managed about what you can do in an appropriate amount of time with the resources that you've got. Now, we've got a lot of resources to help out students. So we've got technical support. So you can actually email us and we'll actually be able to help you out. Again, give us a quick description. Tell us a little bit about what's happening. If you don't have access to the software at the university, you can always download a student version and you can actually start to play around with it. It is node limited, so it is great for teaching, but it's great to really get you started. We've got YouTube channels as well. So we've got a bunch of playlists on things like CFD for FSAE teams, FEA, information about, again, AR and Discovery Live as well, a bunch of different things. I personally find that's the greatest way for me to learn. Everyone's always a little bit different. We've also got blogs as well. So we've got a CFD blog. We've got a bunch of posts and information out there. Some of these, by the way, things like turbulence modeling, I always go back to some of these blogs because sometimes I forget, what the difference between the different turbulence models that are out there and the various options as well. So having maybe some of these bookmarked as well can be really good for your career, knowing that, again, you've got some sort of resources that you can go back to. It could even be things like articles as well. If you're relatively new, maybe your university doesn't have these types of electives, or you haven't quite got to that yet, Ansys, again, have their own kind of learning forums. You can actually go through and learn a bunch of courses that'll really be able to help you out, give you the kind of the backbone and the physics behind it before doing the actual tutorials. And Ansys themselves have their own YouTube channels. So how-to videos, tech tips. We've even got blogs and magazines as well, so you can keep up to date with actually what's out there in the industry. We'll have a look at this in a second. So this is the Leap Learning Hub. I'll log on to it and just show you guys where a lot of the content is actually going to be as well. So this website is actually managed by myself. So this is exactly, this is a part of what we do, helping out students. So we've actually created this website for students, right? Or students and industry. So you can, if you just Google Leap Australia, right, you'll be able to come to us, right, our website. On the bottom right, we've got the quickest link. It goes, again, log into the Leap Learning Hub. Right, again, you can log in on the left, or there's a registration panel on the right. Put your details in. You'll actually get an email with like a password, and then you'll be in here. So this is the front page. Again, what we'll do, a lot of the things that we're going to be talking about and some of the tutorials are going to be on the fluids page. Sorry, I'll just register. I'll just log in. Right, so you can go to the actual page, and we've got a lot of content on there. So you can use kind of the menu at the top to get to what you need to, or you can see here they're kind of organized. So we've got some pre-processing tutorials. Some of these tutorials are actually what we're going to be looking at later on. Right, so these are the space claim. We've also got things like, again, Ansys or fluent meshing, and if you're mechanical, we've got some materials and some contact selection as well. If we scroll down a little bit, you'll start to see that we've got a lot of the different physics as well. So again, I mean, if you've got a project where you need to look at multi-phase flow, best to have a look at these modules. They're not just tutorials, they're also lectures as well to give you a good understanding of the actual physics. And there's some optimization. And at the very bottom, we've actually got some getting started tutorials. So again, we'll be using the fluids getting started, and we'll be using some of these modules. You can see it takes us through kind of what we're going to be doing as well over the next week. A bit of geometry, a bit of meshing help, and then we're going to be getting into the physics, right? Some post-processing. We'll be looking at some best practices, turbines model, heat transfer, and transient flow as well. And then again, afterwards, if you're interested in multi-phase, always good to do the getting started first, and then pop over to the actual multi-phase and then go through some of these materials depending on what your project is. All right. And then the other thing is the Ansys help. So this is pretty much the help manual for Ansys. I use this on a daily basis. If I forget what's happening, if I forget some of the theory or the user guide, or what's the best way to actually apply, a specific model, have a look at the actual help guide. So if you go to your start menu, you'll find this Ansys Help 2020 R2 or whatever version that you've got, and you'll be able to find the Fluent help, and you'll be able to go through some of the material. A lot of what we're going to be talking about, you can actually find a lot of this material, and we actually get a lot of the material from the help guide as well. So again, things like boundary conditions, turbulence modeling, you can kind of find your way through to setting up different models, and again, different various things that I thought personally been very helpful, and I've got a lot of these actually saved out as bookmarks, because again, you're not meant to memorize every single thing, but you should be able to understand how you can get to that, how you can actually get to the information, and again, some advanced stuff there as well. All right, so what we're going to do is that we're going to get started. So everything's just being recorded. Before we actually get started, everyone should be able to unmute themselves, or you can kind of raise your hands. Were there any general questions before kind of getting stuck into it? What we're going to try to do, by the way, is that we've got a bit of an intro into CFD, the modeling process, and then geometry, and then we're just going to get stuck into just firing up an actual space claim and then talking about the geometry modeling process at all. So does anyone, I mean, the people, by the way, if the people that have raised their hands, they can actually lower it. If they want, they can unmute themselves quickly before we get into kind of the crux of it. Awesome. All right. Look, so not many people have any questions. What we can do is just kind of get stuck into it. One sec. Just going to check the permissions, by the way, just to see if there's anything in there that I can do regarding the chat. All right. Not much I can do there, unfortunately. I'll have a chat with with our admin later on just to see if there's anything we can do to get that going. But like I said, if you can actually hop on there, you can send us an email on support. I think everyone should have my email, or you can just find us online. All right, so bit of an introduction into computational fluid dynamics. So what we're going to try to do over this week, we've only got a couple of hours, is that I'm going to try to give you guys an understanding. Well, it's not just myself. I've got Errol helping out this week as well. Give you guys an understanding about the actual workflow behind CFD and some of the best practices as well. We're going to talk about the physics. I'm going to try to not get super deep into the actual physics though, and some of the kind of the numerics behind it. I'd like to maybe keep it focused on the application side of things. But again, I mean, if this is something that you do want a little bit of help with, reach out to us on support. I'm sure we can, help you out, find some documents, find some books, and point you in the right direction as well. Again, if you've got supervisors as well and they want you to do some fluids work for your project, again, reach out to us with your supervisor and we can definitely get on a call, Teams call like this, and really help everyone out. Right. So when it comes to the actual equations, what are we fundamentally doing? We're solving some sort of fluid flow, right? When we're still staying within the kind of realms of physics, right? So we're solving the conservation of mass, energy, and Newton's second law. The purpose of what we're trying to do is get a detailed analysis of the actual situation, right? Things like what the distribution of pressure is, velocity, if we've got multiple phases, right? Like carbon monoxide in the air, what's the distribution of the phases? We can then start to understand a little bit more and get some analytical numbers about things like force, what's the lift and drag on these certain components, what's the percentage, that's the ppm in my actual air volume, and it's used to predict, the fluid flow. We've got heat and mass transfer, chemical reactions, and other related phenomena, and we can start to pair it together with other physics depending on what we're trying to do. It's used throughout the engineering process. I'm sure a lot of engineers at university have used it initially in the conceptual kind of design phase, trying to understand what's happening there. But we use it, after we've got a product. We use it for detailed product development. We've got consultants that use it for troubleshooting. So people often come to them and say, hey, this thing has failed. Can you use simulation to figure out, what are the conditions that had to have happened or occurred for this thing to fail, and then make some recommendations about what we can do to really improve it. And then again, through there, we can optimize the actual design and we can start to redesign our components as well, right? And again, I'm harping on about this, but again, we're here to help. We're not just a sales organization. So if you do have questions, if you have help, reach out to us on support. This is what we try to do, right? So we'll get a little bit deep into the mathematics. Fundamentally, if we kind of take a step back, we've got some sort of geometry on the left-hand side. We're going to break it up into some control volumes, and then we're going to do some mathematics, right? Making sure things like the mass flow in is equal to the mass flow out. Now, in reality, we're using what's called a Navier-Stokes equation, right? So the equation can get pretty complicated, but it can be broken down into these types of terms, right? So we've got some sort of transient term on the left-hand side. So we're trying to capture what the unsteady nature is of the flow. We've got a convective term here capturing the bulk fluid motion of the actual flow, right? We've got a diffusive term here capturing the viscous flow, things like buoyancy effects. And on the right-hand side, we've got a generation term or a sink, right? So if we're creating or removing materials, we can use this term, right? What we're doing with this equation is that we can then start to substitute different variables depending on what actual flow physics that we're trying to involve. And we can actually add equations as well, again, depending on what our actual situation is. One thing I'd like to point out is that solvers are different, right? So even though we're fundamentally solving the same Navier-Stokes equations, how the actual information is stored can be very different as well. So you can see on the left-hand side, Fluent stores the information at the cell and CFX stores it at the actual node. So there are some different ways. So that just goes to show, just because you've got a mesh in a particular case and you bring it over to a different solver, it doesn't necessarily mean you're going to get exactly the same value. So it's important to understand not just the physics, but also how that specific software works in the background. Right. So just walking through the modeling process, we often go around, in cycles when it comes to this, right? We've got some sort of problem identification. So maybe your manager, your team leaders giving you a problem. We need more downforce, right? We then go through and try to pre-process our model. So we set it up for the solution. And we've got a couple of things that we can do there. We then start to solve it, right? And then have a look at our actual post-processing. So have a look at the pictures, the numbers, how does it relate back to our problem, and what are we trying to solve? We then start to review the results, and depending on that, we might then go back and update the actual model. Again, thinking back, are we solving the problem? Do we need to make some changes? Solve, go through that process. It's really important, especially with CFD, before you actually start to even, open the software, is really have a solid understanding about the actual project timeline. How long do you actually have to run your design and, do CFD? How long do you have to actually learn about what you're trying to do as well? What's the current literature? What have people already done? We don't want to be reinventing the wheel here. We want to be thinking about your constraints, right? So if I'm designing, the front wing in this particular car, I know I've got the rules, and the rules say I have to be within, XYZ dimensions, right? Also thinking about what's your system constraints. What are you trying to do? You might be responsible for the front wing, but you'll realize straight away that the front wing affects things like your cooling and your rear wing as well. So then really understanding what's happening there. How are you actually going to manufacture it? Last thing you want to do is make this awesome component that makes a huge amount of downforce, only to realize that you can't actually manufacture that. And you also want to be thinking about your testing constraints as well. So CFD doesn't get rid of testing at all. It simply complements it. So at the end of the day, after we've run through these whole steps, we want to actually test to make sure what we've assumed and what we've kind of designed is what we actually see, on car, on track, or on our component. And you also want to have a little bit of time in there. If something does go wrong, can we make some changes and go back through that process as well? Before, again, we get started, the first thing is to create some sort of matrix, or again, a good understanding about what we're actually going to try to do. What are clear inputs? So it can be input velocities or the angle of attack of the front wing. And what are our clear outputs as well? Do we have like an objective function? So, in this particular case, we'll try to, have this kind of case study where we're trying to maximize downforce at 15 meters per second. So we've got a specific inlet velocity, but we want to, change the actual angle of attack, right? So look, when it comes to geometry modeling, we'll talk a little bit about this, and then we'll actually open up the software and start to play around with it. The first question that we kind of need to ask ourselves is what geometry is actually relevant, right? Do we have existing CAD? Is it manufacturing CAD? Do I need to get rid of and defeature components? Or do I need to create something new altogether, right? If I've got the interaction between, the front wing and the wheel, what components do I need? In this particular case as well, if the air is just going straight on, do I necessarily need the full car, right? I can almost chop half of it and then start to only focus on one half of the actual design. And then again, fully featured, right? So if I'm focusing on the front wing and, the front wing and the wheel interaction is very important, but I may not necessarily need the side pod, the rear wing and the rear wheels as well. Right. So thinking about, how can I simplify my model and my geometry as much as I can? By simplifying the process, it means we can also get more mesh elements in there. We can run more designs. At some point, you're going to need to understand what the interaction is between, say, the front wing and the cooling system. So then, only afterwards, say, would you start to introduce them and put some of them back in as well. The next thing, we're going to be using Space Claim to actually prepare the geometry. So we've got some tools in here to, remove things like missing faces, small faces, split edges, and extra edges. All of these things that we're trying to do is with the goal of creating a nice, clean geometry to create a high quality mesh. It enables us to run our simulations with a lot more accuracy. And we won't have any problems as well. So we won't have any bad quality elements, again, which can influence the actual accuracy of the model. We've got some tools in here to start to remove faces and models, check for things like interference and small edges as well. If we've got an internal geometry, instead we can actually use things like a volume extraction to extract the fluid domain. So we want to, again, always be looking in the fluid domain. And we've got a couple things that we can do there as well. If it's the external volume, so we can look at, again, extracting the external domain depending on what we're after. We've got an example of a car. We'll have a look through that a little bit later on. A couple of things, though, for the external flow you want to be considering is that if we've got a wall very close to the actual geometry, that can actually affect the flow features around here locally, right? So if we've got a wall very close to something, we've got local accelerations, right? So one of the things that you want to be thinking about is, how far away do I need my inlets and my outlets, and my walls from the actual geometry as well. You might want, sometimes you might want to start with a study like this where you've got L, which is the characteristic length of the car. We've got, one length for the inlet, height, and the width, and 3 for the outlet. And then you might need to do a study, increase the actual domain to understand how large does this need to be? If you look at some of the SAE, I think papers and some of the wind tunnel results, I think they assume things like or they recommend something like a blockage ratio of 1 to 5%. So again, you might want to do some research to understand, what applications for that specific industry, might already be out there, and what are the norms. If we've got high speed flows, again, it can be very different. So in this particular case, because flow is only propagating to the right, we don't necessarily need a very large inlet. Right, we've got multiple bodies of influence in this particular case to capture the flow features, and the boundary conditions on the outside, instead of like an inlet or an outlet, we might be using a far field boundary condition. And one of the reasons for that is that with these high speed flows, the pressure and the density changes quite a bit. So just enforcing a velocity inlet may not be appropriate. Some of the things we might need to do again is go in and make some geometry changes. So we'll talk about that a little bit later on. We've got some bodies of influence again we can use as well. We've got some key points here. I'll allow people to kind of go over them at their own page, at their own pace, but we can kind of go through some of that stuff. Right. So what we'll do, just fire up the geometry. While I'm doing that, does anyone have any questions? I think you should be able to unmute yourself. Maybe you can ask a question.
I don't have your email. Could you please type it somewhere in a message?
Yeah,
directly
sure.
to Dmitry, please.
Yeah. Can you see the chat at all, Dimitri?
No.
No? Okay. What I might do, look, what you can probably do actually, if you just do a Google search for kind of Leap Australia,
yeah, I have Leap Australia webpage, of course.
Yeah, you should be able to find the support email address. And if you have any technical questions, pop it on there and it'll actually come to one of our support engineers, and we'll be able to help you out. We try to get back to kind of clients within half an hour to an hour.
Thanks.
So we can get back to you with any questions that you might have. Sammy, do you have any
Hashan, I'm not
questions?
sure yet if you noticed, but I put a message up saying that if you
Yes.
exit and re-enter the meeting, the message icon pops up. So I suspect you have to enter
Yes.
the meeting after you allowed it to be possible.
Oh, okay, that might be what's happening. Thanks for that, Sammy. Yeah, for some reason I can't even see your message as well, so it must be because I changed them afterwards. There might be something going wrong there. Right.
Okay, I will leave it and re-enter.
Thank you.
Hi. I wanted to find out, would we get access to these slides or the
Yes.
later? Okay.
Yep. We'll definitely. I'll definitely send a link out to all the slides as well. What I'll do, I'll show everyone as well. I'm just going to share my screen again. I'll show everyone as well where we've got some of the old training material that we've done, and I've got the material up there as well from that, and the lecture slides are kind of very similar. So again, log on to the portal, register yourself. If you go to webinars at the top, you'll see we've got a bunch of webinars, and I've got one here for online trainings. So again, this is very similar to kind of what we've got at the moment. We've done some other couple of days, so you can see some of the YouTube videos that we've got up here, and at the bottom here with the CFD and FEA presentations will be there as well. After probably this week, I'll try to upload the ones that we're doing here to YouTube as well. I'll send everyone a link, and I'll also try to send everyone a link to the actual CFD presentation here. Send everyone a link to the actual PowerPoint so that you can have a look at that and go through it at your own pace as well. All right. Okay. So I'll just try to have that on the right. Cool. All right. So I've got Ansys Space Claim fired up here. What I did, so I just went to the start menu. I normally just type in Space Claim, and I've got multiple versions here, but I just typed in Space Claim 2020 R2. The latest version that is out is 2021 R1. That only came out a couple of weeks ago. So if you have a look on the Ansys student, you'll probably see that pop up in a couple of weeks. All I did is, in this particular case, by the way, I've got a couple of geometries which you talk through, and I've just dragged it into there, and it kind of pops up with what we've got. Just a quick once over. What we've got is just like a traditional kind of ribbon style system. So we've got a couple of different things that we can have a look at. So we've got sketching tools, designing tools, so push and pulling components. We've got assembly tools, again, measuring. Predominantly what I use is a lot of the repair features. So this is repairing the actual model. Again, using the prepare to create things like enclosures, and then we can start to export them out to Workbench to work on things like Fluent or Ansys meshing, depending on what we're trying to do. Again, additional features on things like sheet metals as well, and there's also some KeyShot plugins, and there's some other plugins you can do and install if you want to create, nice high quality renders. Right. On the left-hand side, we've kind of got our structure tree. So you'll notice that we don't have a traditional feature tree where you can track the sketch and the parameters and things like that. There are a couple of ways to do it using block scripting, but we'll have a look at that a little bit later on. So you'll see on the structure tree again, we've got components. I've named them, chassis, and inside there I've got bodies. Things that are surfaces, you'll notice the components look a little bit different, the icons there, right? I also use things like selections as well, and we'll use that a little bit later on. Really powerful tool because we can have a look at a specific thing, find some holes, and we can search all of the bodies. We can look within a specific volume as well. Right. We've also got things like groups, so creating name selections, which are really important for setting up your simulation a little bit later on. Right. Normally, look, the other thing is that I've just brought this geometry in, so you can bring in Space Claim, CATIA, any files into here, you can work on them, or you can create things from scratch and, create geometry from scratch as well. What I'll do in this particular case is try to set up, a type of simulation and kind of go through it. First thing that we'll have a look at is, look, if we've got a model here, a lot of what we've got down the middle, if we want to set it up as a symmetric model, we may not necessarily need. So one of the things I can do is using my left click, I can select all of them, right click, and suppress for physics. What you notice on the left-hand side is that the icons actually change as well. So you'll notice there's an icon on top of all of that. And what we can do is go right-click, hide everything that's suppressed. What you can see at the top here, from the top views, you've noticed we've got this component that's way out there. We've actually got a surface that's attached onto it as well. What we can do beforehand is we might go through some of these tools, right? So we've got a stitch tool, right? So you can see here, this surface, even though it's come in, it hasn't actually been stitched together. So if we hit the stitch button, you'll notice it then gets converted from transparent to a solid geometry. We can do exactly the same if we have gaps and missing faces as well. So again, we'll notice we've got a missing face up there. We can fill that in. Split edges, so you'll notice again, we've got a bunch of these edges here, right? If I hover over it, again, you know, these edges don't really have any, doesn't really improve the features or anything like that. But you know, if we've got edges that are very small together, sometimes the mesher will put edges, elements between there, which can cause some problems, right? So we can use that to get rid of them altogether. Extra edges as well. Again, you'll notice we've got quite a bit of extra edges. We can select them individually to get rid of them, right? Again, we can select all these. And there are some other times right around here, so where we might want to leave them all together, so we can exclude these regions. And the reason for that in this particular case is that sometimes having an edge that goes all the way across clearly defines what the actual leading edge is of our elements, right? So again, we can select all that, hit the tick button. We've excluded all these regions and everything else has been kind of fixed up, right? The next thing that we'll go, again, we don't really have too many curves or anything like that. Small faces is really important. You'll see on the left-hand side, sometimes what happens is that we can get very small faces that cause problems. So what I'll try to do sometimes is actually increase the size until I know, you know, what my smallest face is or what my smallest edge is. Having all these small elements, again, all these small faces can cause problems with meshing. Yeah, it just requires a lot of mesh elements, and we may not necessarily need to refine this region, right? So getting rid of that can be very helpful. Very helpful, again, if you're not the one that's actually created all this CAD. In this particular case, I'm just going to hide everything else. Because I've created this CAD, I've gone in and tried to make sure things like the minimum element size is, you know, roughly around 3 mil. So when I start to add some sizing, I know exactly, you know, how large I need to have my elements or how small I need to have them. Again, we've got some things like simplify, so we can simplify quite a bit of these features. I'll leave that for now. Inexact edges, and again, I'll normally go through the process and fix all of these up. There are some times where it doesn't quite get fixed up. Right, so you can see here, there's quite a big bulge here, and you can, you know, start to make some changes. You can either go back to the CAD or use Space Claim as well. If I pick up things like the interference tool, I'll pick up, again, we've got, you know, interference between some of these components. It may be something that we expect or not as well. What I'm also trying to find is a duplicates tool. There you go. So I've also picked up this surface here, and I can click to get rid of it as well. Sometimes, by the way, if you're exporting out to something like an STL or like a step file, or IGES is sometimes the worst. IGES sometimes will get rid of faces and things like that, and you can get duplicate faces. So that's why you might need to go through the process of actually cleaning some of these materials up. What I can do as well is, so I've got my aerodynamic components. Again, I don't really need this rear wing or the diffuser. So I can select both of them, and we can just suppress both of those as well. Again, hide what we've got, and we'll leave the remaining components here. You'll notice what I've done here with the wheels is that I've created it on a platform as well. And we'll talk a little bit about that in a second. And okay, we've got some faces here as well. So what we can do is we can select the wheel, right? Or we can, again, select it over here. You notice at the bottom right, I've got an indication of how many bodies I've selected. If we hover over to the design tab, I can use this move feature, and I can actually move it into play. Right, so I can move it roughly to exactly what I want. I can actually take the tool here, and I can move it up to, so I've got some small components here. I can move it up to a specific body if I wanted to as well, right? What I might want to do to make it a little bit easier, I can make something like this transparent. Again, take my component here and move it over to wherever I need to be. You'll notice, by the way, the reason all these things on the left-hand side is that I've created mirror images, right? So I've maintained a mirror component. So you'll notice if I show all the wheels and all the other components, now the actual wheels are back into where they should be. Right. Okay. So now that we've, maybe we've got our geometry set up, one of the things I'd like to do is kind of create my enclosure. So I've got this enclosure tool over here. I can select everything. I can manually specify, what my correct distances, might be. Or on the left-hand side, you can see I've got different enclosure types. I can even give it, like a default cushion as well. So everything's roughly 300%. Right. Now, what I want to do, I need to kind of cut the bottom off. I might want to bring the outside out a little bit, and I can create what's called bodies of influence, which we'll talk a little bit more about in the meshing side of things as well. So I will select both of these axes, hover over to the design tab and create a plane. And I can use my split bodies function here to split that body using that plane. I can get rid of that bottom function, that bottom plane altogether. And then zooming in, you'll notice what I've kind of done over here as well. So if I hide this component, I've got a small radius around, so zoom back out. I've got a small radius around where the tire actually makes contact with the road. If we have sharp angles, it can cause problems for us in the meshing process. So often what I try to do is make sure with some of these sharp contact edges, there's a small fillet around there. Right. And again, I'll take, say, these two faces there. I'll create a plane. If I wanted to, by the way, I can, take that plane, use the move tool, and I could move it up to a specific face, right? Again, use my split body function to get rid of the component on the left-hand side. So let's say, again, I wanted to extend this body out. I can use what's called the pull tool over here. So I can select the pull function and I can manually pull it out, right? So I can specify, how many millimeters or meters I'd like to bring it out, or using some of these tools again, I could, create something like a ruler and tag it on that Y and make sure, I've got a certain distance from the top there as well. When I'm looking to do a fluids analysis, in this particular case, because I'm just interested in the external aerodynamics, I don't actually need any of my solid components there at all. So I can actually go in now and go back and suppress all those components. And if I hide everything, you'll notice I've just got my enclosure, right? So a couple of things that I normally like to do, you can select something like this and go into section mode as well, right? And you can use your tool to go in and kind of inspect. And I often like to go in and just, again, double check. On the right-hand side is where I've got my solid, my fluid domain, and I've got a void there so I don't have anything through there as well. The next thing that I need to do is set up boundary conditions as well, and I'll do that in Space Claim. I'll just make sure all the names are kind of exactly what I expect, right? So I can select that component and create name selection, and I'll normally go through the process of giving it some names. So for this type of analysis, I've got inlet, I've got outlet, I've got the top two here, which are walls. I've got the bottom here, which is the ground. So the reason I'm calling the ground something a little bit different is that the boundary condition in this particular case is a little bit different. I actually want a moving wall. And at the top here, again, I'll call it symmetry. Right. What I often like to do after I've created some of these name selections, I can select them, right click and hide the actual face. And then I can go in and start to make some more changes around here. So I can, again, lift myself up using the triad. I can say select the wheel. make a name selection for the front wheel. And look, I'm not going to bore you, but I'll go through that process and anything that I might be particularly interested in. So I'd make it for the front wheel and the rear wheel. The reason I do that is that I know that I have, I need to give this some sort of rotating wheel, rotating wall component. I'll make it for the front wing as well, because I know I need to pick up the forces on the front wing. You can create a separate name selection for the end plates if you wanted to. And then you could, also pick up things like the chassis and the suspension through there as well. So after you've got that, we've got some name selections. We can then bring it into the actual mesher and we can set up a quick analysis. Right. So this is an external flow example. I've also got a couple of different ones here that I'll go through. So this one is this is the turbocharger, right? So I'll just drag this up to the top. Right, we've got a couple of different things happening and I want to set up the geometry here. So again, with something like this, one of the first things I like to do is go in, create it into, select this section view over here, and you can use the move grid just to get an understanding of what's happening, right? So we've got a couple of models. We've got some things that are kind of offset and it's not exactly what we want to do. So we're definitely going to need to make some changes. You'll notice on the left-hand side, everything's just as solids, and we've got a surface over here as well. So we probably want to have a look at this surface as well. One of the things I'll note, so I'll just make an example. So I'll hide the others. Having these geometries here, when they're just in a component, when they're kind of out in the bare and they're not in their own component, what can sometimes happen is that, especially if they're touching, if I make a design kind of change where I use the pull function, it may automatically merge these faces together, right? Which is not what I want to do. So you can see here, I've got two components here, solid 1, solid 2, and if I make a small change, it will automatically merge together. There are ways using SpaceClaim I can use the no merge feature, but often what I like to do is I like to select the components, right click, and I can move each to a new component. Right, so now that they're each their own component, they're not going to merge when I try to move things around. Right. So just a couple of quirks when it comes to using the software. So again, what I might want to do, go over to my repair tab. Again, I've got gaps, nothing there, missing faces. You can see it's identified a missing face at the bottom. I can select it and you'll notice straight away it converts from a surface to an actual solid. Using my section mode, I'm going to select the Z axis. Right, and I want to align a couple of these components together, right? So I can use in the assembly tab, I've got an align tool, right? So what I can do is I want to pull this out first. So I can left click on one and it will move all of it across. You'll notice even though I'm in section mode, the whole geometry has moved across, right? So again, I can do exactly the same over here. So I can move this in. And on the right as well. So I can, again, move that in. And you'll notice on the right-hand side, again, this needs to be moved in as well, right? So you can go in and start to make some of those changes and start to bring all of these components together. Let's just say I wanted to extract some geometry from there. Maybe I wanted to pull up the internal flow on the left-hand side. I can go over to my volume extract tool. You can see I've got a bunch of different options that I can use. You'll notice, again, hovering over any of them gives me a bit of an explanation. Same so at the top and the bottom as well. So in this particular case, I need to pick up what the capping regions are, and I need to select a seed face. And if I move over, I can see here, I need to specify what my seed face actually is. So again, and click that. And again, using my section view, right? It's X on my keyboard, by the way, as a shortcut. You'll notice it's extracted the fluid. We've got that body over there, and we've got solid bodies as well still inside there. Right, so it's extracted that fluid first for me. Another thing that we can do again, similar to before, if we wanted to look at the external flow in this particular case, we can use things like an enclosure to create around there as well if we wanted to. Right. So those are two things there. What I might do is create this solid elbow. Right, again, I'll do a quick one of this. We'll just extract the fluid. What we'll do in this particular case as well is that we will probably bring it into, we'll use fluent meshing actually to open it up and play around with it. And then we'll create a mesh and we actually bring it over to the fluent solver as well, just to give you guys an understanding about why we want to set up boundary condition or name selections that are appropriate, right? So what we'll do is that we will go into prepare. We want to volume extract. We want to pick face, that one, and the bottom as well. Then we want to pick our seed face and we want to select inside. Right. Again, in this particular case, I don't want to do a conjugate heat transfer or anything like that. So I will suppress the outside body. And we've got our geometry there. Again, on the left-hand side, I'm going to create a name selection. Right, so I'll call this inlet 1. There are a lot of shortcuts inside SpaceClaim, by the way. So if I ever hover over a specific component, you can see there it says Control G, and it allows me to very quickly create something. And if you go to the files, by the way, there is a way that you can specify your own shortcuts as well. Right, and I'll select everything else. So double clicking just selects all my other surfaces. And I'm just going to create that into a wall. Cool. So what I'll do is I'll just transfer it over to Workbench. Actually, we'll start off with probably some Ansys meshing, and then go into try it for Fluent as well. Awesome. We'll set that out, and it'll open up Ansys Workbench for me. So Ansys Workbench, by the way, we use that in order to actually, it's a platform that we can use to build our actual simulations. We can use it to kind of create the steps that we require, and we can start to pull in different physics as well. So you'll notice on the left-hand side, we've got a lot of toolboxes. So depending on the analysis that we actually are looking for. So we've got a Fluent toolbox here. We can drag it over to the geometry. It'll share the actual geometry. We'll set up the mesh in Ansys Meshing, and then we'll hover over to the setup and then go through the solution process. You'll notice on the left-hand side that we've also got additional things, again, if we want to do things like static structural simulations and thermal simulations as well. And we can use Workbench to actually set up multi-physics simulations as well. So you can see here when I hover over it, I can transfer over the geometry as well as the results from my fluids analysis and apply a structural analysis as well. For now, I'll just delete that. All right, just save this off. Oh. By the way, I don't think the whole session is going to go towards 12. I just wanted to make sure that we had enough time. I think the geometry and the meshing is relatively quick. Right, we can probably get through it within an hour and a half. With Errol coming in though afterwards, where we're going to talk a little bit more about the solver, that might take a little bit longer. All right. All right, so we're just going to be starting up physics. We'll dive into a little bit more detail, by the way, about the different meshing technologies and the meshing elements that are available in Ansys Fluent, and some of the actual different softwares that we can use in more detail tomorrow. So I'll fire this up and we'll kind of set it up and get it going, but I won't go into too much detail. All right. So we can see we've got Ansys meshing here. Name selections have all come through. We can create name selections in Ansys meshing if we wanted to. On the meshing, you can see on the left-hand side, I've got a couple of global features. So the physics that we've set is Fluent. And you can see here, because it's a fluids analysis, we've got some defaults for the global sizing features. I'm just going to go right click and generate a mesh. All right, so you'll see the default mesh that's created is this tetrahedral mesh. And if we go over to the selections, what am I looking for? The section plane, we can take a cut through the middle, and you can see the kind of the mesh that's been generated. You'll notice there is a lot more refinement around this area. It's because we've got a smaller inlet. We've got a lot more radius again around these regions, and we can use these sizing features on the left hand side in order to actually refine that as well. What we'll do is that we will also add inflation. So inflation is they specify boundary layer elements, and they're used to accurately predict what the actual boundary layer is doing, right? And you can see here the way it does that is that it creates these prism elements, right? And again, we'll talk a little bit more about that in the meshing, and Errol will actually go through some of that process as well in his sessions as well. Right. After we've done with that, we'll just go right click and update the actual mesh. And we'll go over to the setup, right? So we'll use the double precision solver. In this particular machine, I've got 4 CPUs. You'll notice, by the way, if you need to, you can check out some of those resources, some of the Ansys resources on the left-hand side if you're having any problems. And at the bottom here, you've got the help. It's got kind of quick access to some of the help menu and some of the help options as well. And we'll fire up Fluent. Apologies, guys. We've got a couple of problems here. So I'll just close it down and open it back up again. Let's reset that. Save button again. And I'll open this setup again. Hopefully this one works. If not, we'll open it just a different way. Awesome. All right, so I'm just going to set it to default. I'll just bring up the console as well. So the console, by the way, is just, it writes out exactly what I'm doing. So this is Ansys Fluent. So again, similar, we've got a ribbon style where we can go through the process and the steps to set up our actual simulation. And on the left-hand side, we've also got an outline view. And I'll step through the outline view just because that's just what I like to do. It makes sense to me. But the training will show you kind of both ways to go about it. So what we'll do is that on the models, we'll notice that the K-Omega SST turbulence model has been set by default. Again, Errol will go over the different turbulence models and some of the different other models that are actually available. And if this is something that you want to, you're interested in, again, let us know. We can go into that in a little bit more detail offline. On the fluids, again, we can double select our materials and we can, inspect the actual properties of the materials. I can create a new material if I want to, so I can manually put in the components. Or if I hop over to the Fluent database, you'll notice we've got a bunch of different materials that we can directly import into. On the left-hand side, again, we've got just a single cell zone, and we've got some boundary conditions. So now this is why it's really important to have appropriate name selections. You'll notice that the name selections have come through, and it's automatically identified it as a velocity inlet. If that was incorrect, I can right click on it and actually change the type, and we can see we've got a bunch of different velocities that we can implement. So what we'll do in this particular case is just set up a velocity inlet of 1 for one of them, and we'll just increase the velocity for the second one, and we'll leave the pressure as is. Right, so we'll leave that. We've got our solution method. So these are some of the discretization methods that we were previously kind of talking about. And actually what I'll do, look, normally I'd set up some report monitors. Actually, we'll do that. We'll set up we'll set up like a surface expression of what the area weighted average is. And we'll have a look at what the area weighted average of the outlet is. And we'll look at things like the average velocity might be. We can also look at things like, say, actually, let's just pick up mass flow rate at the actual outlet. And we'll create a report out of it and print to console. All right. Go over to the run calcs. We'll give it like 100. Actually, and we'll just hit the calculate button. Right. So what it will do for us is it will initialize the solution for us. So it will, give it values, and then it will actually start to solve. So we can visibly see we've got the mass flow rate, so we can see how it's changing with the iterations, right? And we've got the residuals as well. So we can see the residuals are dropping, and we've got mass flow rate that is flatlining, which is exactly what we want to see. What I'll do, I'll let this go for a little bit. You can see visibly as well on the console what the actual values are and what's happening. So after the simulation's finished, right, so you might want to have a look at some of the different key values that you might be interested in to understand if you've got a converged solution. Have a look at things like the residuals. You may even need to do things like a sensitivity study as well. But what we can do, so we'll just show the mesh. Right, on surfaces, I can right click and click a plane, and I'll create it on that, and we can hit create. Right click on things like contours, and we can have a look at what the static pressure is on that plane. Right. We can have a look at things like vectors as well. So if we put vectors on the inlet surfaces and the outlet surfaces as well. Right, we can also have a look at things like path lines, right? So we can show what is happening if we release some sort of path lines from, each of these inlets over here. Right, we can color them different ways as well. So let's color these by velocity. Right, and we'll create I just want to get rid of, we'll just have the walls here. And what I can do then afterwards, right, if I wanted to take a nice picture, I can select the mesh and all these components, right? So we just increase the transparency of that. We can start to inspect what's happening in this process and have a look through some of the components as well. If we look at our reports, we can pick up things like surface integrals, so we can look at what the actual mass flow rate is on the outlet, as well as the other two, right? So we can see what the sum is, and we've got a report of it as well there as well. So that's just a quick overview of setting up kind of Ansys Fluent, and then going into setting up the geometry in Workbench in SpaceClaim, working through some of the different components, like an external flow example and like an internal flow example here, playing through some of the tools, creating things like an align tool, and also some of the repair and the prepare functions as well. And then bringing it over to Workbench, creating a mesh, and then setting up and running, a quick simulation as well. Right, so we're able to get through most of that stuff in a couple of hours. What I might do as well, I'm just going to create a new kind of component. One of the things I wanted to show you as well, maybe talk about, is just some of the tools that we've got inside here as well. Look, I don't want to spend too much time, but we can use, some of the sketching tools as well. So if I select that rectangle, again, you can go in and start to create kind of something. We can then go over to the design tab, use the pool, and using that sketch function, we can pull it up, right? Again, if I wanted to, I can select a surface, right? Use my pull in order to actually pull through that surface as well. And we can create these types of components. So, the other great thing about using SpaceClaim is that, built off that surface, you can take that, copy and paste the surface, and then we've got that already created for us. So I can actually fill that in using the fill tool here, fill in this one, and it converts it to a solid. Use things like the move tool and kind of move it across, and use my pull functions to kind of pull them out as well. If I've got that type of geometry, I can actually combine it together. So again, select both of these components and combine them, right? If something's gone wrong, it'll normally give me a bit of an explanation about why in the world these things can't be combined. That's right. Or we could use, say, like the split body function. So I can split that from that body. And now you'll notice if I hide that, I've got these two additional faces here that I can start to remove as well. What we can do is also use the pull tool to select an edge, and we can create things like rounds as well. So we can zoom in, make what we're after, or specify the round. And you can see we've got a couple of additional tools as well. So we can create a chamfer if we wanted to. We can take that edge and we can extrude it out in a specific direction and then start to pull down on it, make it exactly what we wanted to, and kind of play around with it so we can use some of these features. Right, we can say take that edge over there as well. So again, we can copy the edge, right? And we can pull it across, and we can, build off the geometry if we wanted to. Right, so depending on what you want to do, you can, create this geometry from here, from scratch, or you can import it in. Having a look at the block scripting as well. So you'll notice, by the way, on the left-hand side, I don't really have any feature tree, so I can't go back. So I'll have to Control Z. But with the block scripting, it actually does start to record some of these features as well. So let's just say I go over to the top here. I use my sketch function, and I can create a rectangle, and I'll create this rectangle here, and I can give it a dimension as well. Right, so you'll notice after that sketch is created, I've got a couple of dimensions here, and I can go back, to that component. Afterwards, I can go in and then use my pull feature to cut through that. So again, you'll notice that extrude face has been picked up. And I've got a couple of things that I've done here. So it's pulled it through at a specific distance as well, right? And then if I wanted to, I could go back to, say, this feature here, make it 15 mil instead, and it'll regenerate that sketch as well as regenerate that, that pull feature as well, right? So what you can do is kind of, depending on the complexity, you can use some of this, inherent block scripting in Workbench to script through a bunch of different cases, different meshes as well. Right. Okay, so look, those were the main things that I wanted to address and go over for the first section. Hopefully everyone's got a good understanding about what you can do with SpaceClaim. What I'd recommend is that if you've got some time, hop over to the Learning Hub, go to Fluids. There's a Getting Started Fluids, right? And if you go to the very bottom, it'll go there for us. You can download all of the modules and the videos there, and you can try the first couple, right? So module 1 just talks through some of the core skills using SpaceClaim. Module 2 is about creating geometry. You'll notice the repairing geometry, so that's what I was playing around with, and some of the external flow features as well. And if you want to set up parameters, you can also do that as well in module 5. The overview, again, and we'll go through some of these stuff a little bit later on. Right. So those are the key things that I wanted to go over. Hopefully everyone's got a good understanding about what you can do with the starts of CFD, what we're doing in the background, some of the geometry and pre-processing features that we can do within Ansys, and how we might need to actually clean up our geometry as well. So tomorrow we'll focus on meshing, and then afterwards we've got Errol that's going to come in and talk a little bit more about the actual solver and some of the numerics and some of the mathematics behind it, as well as the post-processing side of things as well. Cool. All right. So look, if anyone wants, they can unmute themselves if they have any questions at all.
So you've missed a few questions in the chat. I could, since you can't see them, I could read them to you if you wanted.
Yes, please. Can you please do that?
So the first question was, why space claim? Why not design modeler or ICEM CFD?
So what you can do. So I personally use SpaceClaim just because I think it's a modern, it's an easier way to do all of these. Design Modeler does have its benefits where because there is a feature tree there, it's a little bit closer to the SolidWorks and the CATIAs of the world. But personally, it hasn't quite been improved. It doesn't look as nice and as flashy. And SpaceClaim has a couple more features as well. ISIM's just something that I personally haven't used too much of. But from my understanding, we can't use a lot of geometry prep in ISIM. We generally recommend SpaceClaim just because there are a lot more features and tools, and it's what's going to it's going to get updated quite a bit with exactly what we want to get out of it as well. Yeah. What I might do, yeah. Do you want to, next one? Sorry, I don't want to leave
file
it.
formats can be imported? For example, can 3D scans be imported as STL?
Yes. So if we go to open here, we've got a bunch of different file formats. Pretty much anything what most people want to do, even like Revit files and things like that, can actually come into SpaceClaim. So SpaceClaim has its own reader as well, so it will automatically read it in. So you don't necessarily need to export it out into a neutral file format and then bring it back in. When it comes to STLs come in as well. I think with 3D file formats, the one thing maybe we want to talk about, if you've got that, is point clouds. I don't think we can import in point clouds at the moment, but I think it might be something we can do with some other software here and there. Yeah. Any other questions in the chat?
Yep, you're getting even more now. Do you want to try and make your
Well, yeah.
chat,
What I might do? Give me a second. I'm just gonna I'll stop sharing. I will ask one of my colleagues to come in here and log on, and I'll get him to see what's happening there, and I might read his thing. Give me one tick. All right, give me a sec, guys. I'm just gonna pop back. Hey guys, back. Sorry, just trying to see what we can do here. There you go. All right, so the chat's coming up now. All right, so, sorry. So everyone said good morning. Good morning to everyone. Yep, download access. So it talked about that. So with some of the geometry, by the way, so that's just geometry that we've worked on before. If you're interested in any of that stuff, it's all just FSA geometry. I can send that out to everyone. Yep. So that should be fine. Again, CAD formats, same. So Sammy, if there's anything particular that you're looking to import in, let me know. Small radius or so heuristics about producing geometry is better to have small radiuses than a sharp join between surfaces, for instance. How sharp is a sharp join? Yeah. So Angus, generally what we want, yeah, sharp angles can cause us problems in the mesh generation side of things. Having a sharp angle can make it difficult to get good quality elements in there. So for instance, when you've got that, we generally want to go in and start to add a small radius. What happens is that by adding a small radius, though, we start to increase the number of elements that we've got around those regions. So our mesh count goes up. That inherently means that our mesh times will go up as well. It might be one of those things that you might need to do some analysis depending on what you're trying to do. Sometimes, if you have bad quality elements and if they're far away from what you're after, you could potentially get away with just kind of leaving them. But generally, when it comes to high quality simulations, we always recommend going in and cleaning them up. Sometimes it does mean making changes to the geometry. And it's one of those things. It's an engineering decision about, is it appropriate to go in and make those changes, and what else can we do? For the wheel example that we were previously having a look at, that F1 wheel, the Formula Student, wheel, having those radiuses don't, change the flow structure. But in reality, the tire deforms quite a bit, and that deformation of the tire can change the flow structure coming into the the diffuser as well. That's one of those things where I was a part of the SAE competition, and last year there was a team from Poland that had a whole final year project about actually pumping up a tire, deforming it, scanning the geometry in, bringing that geometry, and then doing an analysis between having a fillet or having the actual geometry, and they actually found some large differences. So it might, again, it's one of those things you might want to have a look at what the actual literature is out there, and if you're not entirely sure, maybe make some small test cases, and a lot of that's and get an understanding, have a look at the results, and then start to compare between the two of them. Again, similar way, if you've got bolts and nuts and things like that, you got to ask yourselves, from an engineering perspective, is this going to actually have major effects on my flow, right? Can I get away with it? It also comes down to what are your timelines. Having a lot of mesh elements can make it simulations run a lot faster. So understanding that is really important as well. Yes, Inventor models can get brought in. And yes, you can import step files in as well. Hand enclosure for a cylindrical enclosure. Yeah, sure. So let me just share. Let me just share my screen again. Right. So as an example, if you had, actually, let me just see if I've got geometry that might have some cyclical components to it. And I'll show you how we could potentially set something like that up. Go to Rocket. Okay, so I don't have anything quite on me at the moment. So, I mean, if we start something new though, I'll just use a block and I'll just show you how to set something like that up. If we've just got a block here, we'll just create our component and we'll pull it up. right? So we've got two ways of doing something like this, right? So if we go over to the Prepare tab, we can select the enclosure and we can type something like cylinder, right? Just for the purposes of this, I'll just make it small just so it's easy to manage, right? And let's just assume we've got something in there, maybe it's a blade or something like that, and we want to make it cylindrical. We want to give it some sort of cyclic symmetry. So what I would normally do is select my two angles, or you can use the mid plane there, and create an actual plane. You can select that plane and then use the move tool. If you hit Control, you can create a duplicate of that. Right, so let's just say we've created a duplicate there and we want it coming in at around 45 degrees. Right, we can then use the split body function and we can get rid of some of these components here. So again, I've got rid of, slice them together, and again, using the one at the top here. Right, then we can hide these two. Right, and we can probably hide the solid geometry if that's not something that we're particularly interested in as well. Right, and we've got this kind of sector model. Right, what we do is that we might have, say, some sort of inlet, an outlet, and symmetry at the top. And then for this cyclical side of things, we would give it a name selection, right? Period 1 and then period 2. And in Ansys Fluent, in the actual solver, we could actually tell the software this is cyclical, and there's an actual boundary condition for that as well. So that's how you pretty much set something like that up. Depending now on what you want to do, though, there might be a couple of things. So if it's like a blade, or you want to do turbo type of machinery, there are separate ways that you might want to set it up. So it's one of those things, maybe before you go through the process, have a bit of a chat with us to understand exactly what's happening, what exactly you're trying to do, and it might be good to help you out there. Cool. Awesome. Is there any more questions at all?
Yes, I have a question that how to draw a random shape using a space clamp.
Yep.
For example, the tree root in a pipe.
Sorry, can you say that again? You're a bit faint there.
Yes. My question is how to draw a random shape using space clamp. For example, tree root in a pipe. For example.
What in a pipe? Sorry.
Tree root.
Tree root. Oh, okay.
Yeah.
So
there.
I guess there's a couple of ways that you can do something like that. I mean, you can use like your sketching, your sketching tools here. We've got splines, right? So features like splines. So depending on how good you are, you can create your spline like that. And let's just say we can take that line and we can pull that line up into a surface, and then we can extend that surface and create, an enclosure. We can create a solid. Right. We can import geometry in if we wanted to as well. So if we've got import from other places, or the other way to do it is that you can import what's called a polyline in. So a polyline is essentially a text file with a bunch of coordinates for the kind of the X, Y, Z, and it can automatically create this, this spline for you. All right. So then when, we've got something inside there, you can then again go in and let's just say you want to remove it from something. Right, so let's just create say we've got something like this. Want to extend it out. Right, we want to hide it. We can go back and use our split body tool here. So we can use that, get rid of, sorry, use a combine tool, and use that as the cutter and get rid of that geometry. Right, so you can see it's created two of those. We can delete that. So now if you take like a section view through there, you can see the geometry that's been created and how it's been taken out of that actual component. Yeah. So it would be playing around with like the line, rectangle, spline tools here. We've also got a 3-point arc. and you can bring that in. I've also had, if you've got like a PDF as well, you can bring in a PDF. You can kind of resize it to however you want, and then when you've got an actual picture, you can then overlay the spline tool or the line tool, or one of the kind of create functions in here to actually to generate that shape. Right, and then again, you can either create the line, like I was showing you, extend it out, or you can, cap the surfaces and create those components.
Thank you.
Does that make sense? Yeah, awesome.
Yes.
Cool. Any other questions in the chat, or you can unmute yourselves as well and you can ask. Cool. Okay, look, if there aren't that many other questions, we can close the session for now. And you can always, reach out to us on support, and we can help you out with anything. So tomorrow what we'll do is we'll have our session. We'll start with meshing, and we'll talk about what we can do with Ansys meshing as well as Fluent meshing as well. By the way, I mean, if you're going through all this stuff, you do have a request and you want more advanced physics. So if you want, one of our senior applications engineers to talk about things like multi-phase, discrete particles, and other advanced physics as well, let us know. We are organizing some more training over the Easter break coming up. I know we've got some people that have been interested in some crash analysis. So if you do, let us know. Maybe just send us an email and say, hey, this is what you'd like to do. I can always take that and go to my manager and say, hey, we've got plenty of people that are interested in this type of training program. We can organize something for everyone. Awesome. All right, thanks everyone. Thanks everyone for coming along for the first day. I will see everyone tomorrow. All the video lectures, we'll try to get the CFD ones up by the end of the week, and we'll send everyone a link. And then what we'll try to do is again, we'll talk to everyone on support, and if you need any help, feel free to shout out as well.
Hassan, just before you leave, just a quick one, man. Are you okay?
Yep. Go for
it. Just regarding, I'm not really sure if this is the right session to ask the question, but hydrodynamic forces, and the differences between aqua and fluent.
Yep.
Are you in a position to answer that, or?
I haven't played around too much with aqua, to be perfectly honest. What you might maybe ask, send the email to support. I've got Sam Nadala, which is one of our senior applications engineers. He's done quite a bit of work with aqua. But I mean, shoot the question. Maybe you might be able to answer it.
No problem. Thank you.
Yeah. Well, do you want to ask the question now, and then I'll see if I can answer it. If not, you can just send a message.
My question is more generally about the hydrodynamics forces modeling for underwater vehicles, and in terms of modeling the drag and the mass of the forces that occur underwater.
Yeah.
There is no specific question. I'm generally interested in how to calculate the added mass values and the drag. Non-linear drag. So I know there is ways to model it in. It's a bit confusing whether to use Fluent or Aqua, and that's more of a general question, really.
Yeah. Look, if that's what you're specifically after, I think that does sound like a Fluent problem, because you want to actually want to solve the Navier-Stokes equation to pick up what the actual flow features are. Whether is it pressure drag, is it skin friction drag, and Fluent allows you to actually do that. From my understanding, Aqua is a little bit more on the structural side of things. Like, it doesn't actually solve the Navier-Stokes equations like Fluent does. That being said, there may be some assumptions, and maybe some ways that we can get around it. So look, I mean, still send that message out. I can have a quick chat with Sam and see if Sam does have any suggestions or if there's ways around it.
Yeah. No, I appreciate that, man. Thanks. So I'm probably going to delay sending a question out more until I probably get a little bit more specific question that I have. And I'm actually been playing with the software, so I'll keep it in mind that I can just go to you and ask when I need to, but I'll probably leave it until I have a more specific question.
Yeah, no issues at all, mate. No issues at all. Easy. Anyone else? Is it Fan? Do you have a question there? Is it Lefan? Okay. Anyone else with any other questions?
Not at this stage, Harshan. Thank you very much for your time.
Oh, hi there, Prasad. Thanks,
Hi.
Thanks a lot.
No worries. I'll see you tomorrow.
No issues. See everyone tomorrow. Take care, everyone.
Bye.
Bye.